So again, let's notice the difference between the two models, the continuous state Markov model, or the Kalman filter, or the linear Gaussian Markov model, and what we discussed last time, the hidden Markov model, which was a discrete state model. In both cases, we have exactly the same graphical model representation. We say that the distribution on S2 is only dependent on what happens with S at time 1, and that at any given time point, the observed vector, the observation at that time point, is conditioned only on the latent state at that time point. So we have exactly the same graphical representation for both the discrete state and continuous state Markov models. The key difference is that the distribution on S2 is a continuous probability distribution given S1. Whereas with the hidden Markov model, the distribution on S2 was a discrete distribution on S possible states given the state at S1. So the hidden Markov model had a discrete distribution on each of these states. The continuous state Markov model has a continuous distribution on each of these states. And these continuous state Markov models, the linear Gaussian Markov model and its many variants, which we'll discuss at the end, have many applications. Primarily, they're used for tracking objects. They're also used in automatic control systems. They're used in economics and finance, for example, to model stocks, as well as other applications. So let's look at a concrete example before we become more abstract in deriving the algorithm for the Kalman filter. So here's a classic, very specific tracking problem. We're assuming that what we get are noisy, and we're going to assume very noisy measurements of an object's position as a function of time. And we're going to assume that we're taking these measurements high up, so we can model them as being in R2, just an xy coordinate. So at time t, we get a two-dimensional vector that gives a very noisy measurement of the location of an object in a two-dimensional plane. The underlying state vector, which is also a function of time, is now going to be a six-dimensional vector. So this is the unobserved state. And each dimension in space in the measurement corresponds to three underlying states. For the first dimension in the observation, so for say latitude, we have the position as one of the latent states. We have the velocity and the acceleration in that dimension, in that direction. In the other direction, we say longitude, we have the position, the velocity in that direction, and the component of the acceleration in that direction. So for the two-dimensional locations, we have this six-dimensional latent state vector, which we don't get to observe, which has the position of the object encoded in it, as well as the velocity and the acceleration in the two dimensions. Okay, so now motivated by the underlying physics of the problem of motion, we model this as follows. We say that the state vector at time t plus 1 is equal to this matrix C times the state vector times time t plus some random perturbation. And for this specific problem, we choose C, again motivated by the underlying physics, to have this exact form. So notice what this is modeling. This first dimension corresponds to the position in the first dimension of the object. That's equal to mapping again to this vector here. That's equal to the position at the previous time point times the amount of time that is passed. So we're going to make the assumption that the sampling time is discretized, say every few milliseconds. And so the amount of time that has passed since the previous time point times the velocity. So this is the amount of motion that has taken place in the direction in the interval from time t to t plus 1, which has this delta t amount of time lapse, plus 1/2 times the time lapse squared times the acceleration. So what this these three values are modeling is the position as a function of the previous position, the velocity in the first dimension, and the acceleration in the first dimension. These three values multiplied by these three values will give the estimated position at a time step delta t in the future. If we look in the second dimension of the state vector, that corresponds to the velocity along the first dimension of the observed space. So for example, this could be the velocity in one direction, in say the longitudinal direction. That's going to be equal to 0 times the position at the previous time point, which makes sense. Position doesn't impact the velocity. Plus 1 times the previous velocity. So this says that the velocity at the next time point should be like the velocity at the previous time point, plus delta t times the acceleration. And so that takes into account how much we're speeding up or slowing down at the previous time point. So we have the velocity at the next time point factors in both the velocity at the previous time point plus the acceleration at the previous time point to give a prediction of the velocity at the next time point. And then finally, for the acceleration along that first dimension, we're going to have this dampening effect that says that the acceleration should always be either decreasing or increasing towards 0. So this is a dampening that takes the old acceleration, it multiplies it by a number that's slightly less than 1 to dampen the acceleration. Okay, so this is the underlying state vector. And then the observation is simply equal to this matrix D times the state vector plus noise. Notice that all this matrix D is doing is picking out the position along the first dimension and the position along the second dimension of the state vector to then say that the position is equal to whatever these two values are equal to plus noise. So this is a simple Kalman filter for modeling a moving object, where we're going to try to then use an inference algorithm to both predict where the location is as well as predicting what this underlying state is. So this predictions for these underlying state vectors will not only capture the position of the object, but also the velocity and the acceleration of it as a function of time. All right, let's look at an example of what we would learn from this algorithm on tracking a real moving object. So we're going to discuss the actual algorithm in the second part of this lecture. First, I want to show the results. So what we have here in these 4 time slices, I'm showing this solid red line, which is the same at all 4 time points. This is the actual trajectory of the object as a function of time. So I'm showing the entire trajectory of a particular object. The black dots are showing the measurements at various time points. So I'm showing all of the location measurements of that object. You can't tell the ordering of these measurements from the way that they're plotted, but you can tell that they're very noisy measurements. So on average, the measurements are following the location of the object, but they're very noisy. So for example, at this point, when the object is right here, we might have measured the object as being right here, but at the next time point, when it's right here, we might have measured it as being way over there. So that's the noise in x. So again, these dots correspond to the measurements xt here. And the noise is fairly large for this problem. Now what I'm showing in these 4 slices is the state vector at that specific time point. And I'm not showing the entire 6-dimensional state vector, I'm just showing 4 of the dimensions of the state vector. I'm showing the first and the fourth dimension as the red dot. So remember, the first and the fourth dimension correspond to the position in the first dimension of the observation space and the second dimension of the observation space, so the position of the object. So that's what this red dot is. And so we can see that as a function of time, we're accurately measuring the position of the object so that we're averaging out the noise. And then this blue line is showing the velocity vector. So I'm plotting a vector of this velocity in dimension 1 and the velocity in dimension 2. That's the blue line, which gives us a estimate of the direction and the speed in which the object is moving. So the speed actually is the length of the arrow, and the direction of the arrow is the direction the object is estimated as moving at that time point. So we can see that as a function of time, what we're learning with this tracking model is both the location and the direction and speed of the movement of the object as a function of time based only on these black dot measurements.